Here is yet another version of our rectangle class. And I'm not saying that because that's a bad thing, because obviously we've got, I guess, at least 2 weeks left of talking about shapes. We're going to see a whole ton of other rectangle classes before we're done. But for now, here's another version. And this version combines together a whole bunch of features we've already seen and drops in a couple of new ones to sort of complete some things, to tie up some loose ends that we've brought up over the past few videos. Okay, so we have our class rectangle, and recall the overarching theme of the past few videos has been that when I define one of these classes, my goal is to have complete control, to be able to exercise however much control I want over every object of this type. We can choose to exercise almost no control, but I'm given the opportunity to exercise complete control, including things like how the object gets created and who can create it. So we'll start there. I have a series of constructors, and recall that if an object, if a class or struct defines any constructors, that means that when you create such an object, a constructor must always be called. Which means if I were only to define, for example, this constructor here, the constructor that takes 2 double arguments, if that's the only constructor available, well, there is at least one constructor, so a constructor must always be called. And that means that if this is the only constructor available, you are not allowed to create a rectangle unless you provide an initial width and initial height. If you provide no constructors, really we interpret that as the compiler providing you a free public default constructor that does nothing. But here I've defined my own default constructor, and this default constructor is in the private section. So that means that nobody outside the class may call this constructor. The effect of that is, in main, you are not allowed to create a rectangle without providing some kind of constructor arguments, because that would require calling the private default constructor. We saw that as an aside in a previous video. Down here, I have one of the public constructors. I'll call this a parameterized constructor because it takes parameters, and it takes an initial width and initial height. And this constructor enforces that the width and the height must be greater than 0, so that it's not possible to have a rectangle with negative width or negative height, or 0 width or height. And it also uses this syntax to construct the members. So this class contains a member called width and a member called height. And although we are allowed to set them using assignment statements, this is using the syntax to construct the members initially, to actually dictate how they are initialized. It does that by initializing the member width to be the initial width that was provided. It initializes the member height to be the initial height that was provided. And then down here, it asks whether the width and height that it now has is valid, and otherwise it throws an exception. Note that although I am initializing width and height before the constructor begins, if I end up discovering the rectangle is invalid, by throwing this exception, that means that the construction fails and the rectangle object no longer will exist. We know that because if the constructor throws an exception, the line that I was calling the constructor from will just bail out of that line. So if we're in a try block, we'll catch the exception, otherwise the program will end. And therefore the rectangle can never be used. So here I have the sort of obvious constructor for a rectangle. Down on line 36, I have added this meaningless, contrived constructor that does something sort of ridiculous, just to prove I can define as many constructors as I want. This constructor takes a string. And then, as you can see, it does nothing with the string. But because this is a constructor taking a string, if I call the constructor with a string argument, I will end up in Parameterized Constructor 2. And this sets width and height to be 10 and 17. Deliberately, this constructor doesn't use the syntax I've used up above, just to show off 2 different ways I could choose to set width and height in constructors. On line 43, we've got something new, something we haven't seen until this video. This is called a destructor. So just like a constructor governs how the object enters the world, a destructor governs how the object leaves. Now, although I have lots of control over how my objects are created, so when you are allowed to create a rectangle, who is allowed to create a rectangle, all of that can be dictated by constructor semantics. It turns out you can only define one destructor. And that's because although you have control over who's allowed to create a rectangle and when it's created, once a rectangle exists, there will come a point when its lifespan ends. Every rectangle that exists will eventually be destroyed. And you don't have too much control over when it's destroyed, because when a rectangle gets destroyed is subject to things like the rules of scope. As a result, you can't, for example, demand that when a rectangle gets destroyed, somebody provides arguments. You may not have control over when the rectangle gets destroyed. However, you do have some control over what happens when it gets destroyed. So you don't get to decide when, but you do get some control about what happens. And so you can define what's called a destructor. And destructors must always take 0 arguments. Their syntax is the word rectangle, so the name of the class, preceded by this. This is the tilde symbol, so you'll find it probably above your tab key. That's a bad drawing. It looks sort of like this squiggly line. So why do we use this? In C and C++, this symbol is also used as an operator. It's actually the Bitwise Not Operator. Now, you probably haven't spent much time working on bitwise operators if you just took this course in CSC 111. There's also the logical not operator. And we recall that logical not is a way of flipping a true value to false and a false value to true, sort of flipping a value, inverting it. The bitwise not operator is used for flipping bits, so 0s to 1s, 1s to 0s. We don't care that much. I believe that the reason this symbol was chosen as a way of indicating destructor was by analogy to the not operation. So this is what brings the rectangle into the world. This is sort of the opposite of that, just like how the not operators turn a bit or a logical value into their opposite. I think that's where that came from. In any case, we're stuck with it. This is the notation we use to define a destructor. And pretty much every destructor ever looks like this. There's one other thing that could appear in the signature of a destructor, an extra keyword that we'll see in a couple of weeks. But in general, destructors never take any arguments. So if a destructor is defined, then under normal behavior, whenever an object comes into being, we construct it. A constructor must always be called if a constructor exists. And if a destructor exists, the destructor will always be called when the object gets destroyed. So the destructor gets called just before the object's memory is deallocated. So just before the object is thrown in the garbage, we call the destructor. And we'll talk more about that next week, because there is a question of when a bunch of objects get destructed, what is the order of destruction? And we'll begin talking about that in this video, but we're going to come back to that next week. Okay, down here I've got a member function called print that prints out the width and height of the rectangle. I've got my getWidth, getHeight, and getArea functions. I haven't added the const keyword to these. We'll come back to the const keyword later, but these are getting the width, height, and area as in previous examples. Here I have my static member function, createUnitSquare. Recall that a static member function is an ordinary function that is allowed to live inside the class. That means that although getHeight and getWidth work on a specific instance of rectangle, I call getWidth on a rectangle, I can just call createUnitSquare whenever I want. I don't have to have a specific rectangle that it's associated with. Now, it doesn't mean createUnitSquare doesn't get any benefits from living inside the class. It does get the benefit of having member access. Because it's inside the class, it gets all the same access to any rectangle that it encounters. It is allowed to use the private members of, like width and height. And in fact, on line 65, when it constructs this rectangle, it is calling the default constructor, which the outside world is not allowed to call. But because createUnitSquare lives inside of the rectangle class, it is allowed to call private things, so the private default constructor. And then finally down at the bottom, I've got my private members width and height. In this example, I have not added curly brackets to their declarations. I don't actually have to do that, and there's an argument that one could make. Many people that have watched these videos that might know a bit of C++ have wondered about this. Why do I keep providing initializers for members if I later have a constructor construct those members? To avoid confusion, often we would see no initializers given here as a way of signaling that no, the constructor's in charge. It will make sure the members get initialized. Either is fine. If you have an initializer here, it is superseded by the constructor if a constructor gets called. All right, and then down here I have main. In main, I create 3 different rectangles. I create one with the parameterized constructor that takes a width and height. I create one with the constructor that takes a string, and I create a third one using createUnitSquare. So what this is doing is calling createUnitSquare and then setting R3 to be what we can think of for now as a copy of what comes back from createUnitSquare. We're initializing R3 to be a copy of another rectangle. We're going to talk a bit more about what copy actually means. I mentioned earlier in the course that that is a bit of a thing in C++. We're going to talk more about that next week. Okay, so then I print out R1, R2, and R3, and then I print out done main. This is because I want to show off an interesting thing that happens after line 94. I guess I also want to just put a bookmark here. You might also see a line like line 83 written like this. This would be a C-style initialization. This looks a little bit more natural when we're setting a rectangle to be the result of a function call. But to be clear, because we know C-style initialization can be rewritten with curly brackets, it's actually just a special case of this. So I'm calling a function, taking its return value, and then setting R3 to be that. To be a copy, well, to be a copy for today's purpose of what comes back from this function. Although again, I'll come back to what copy means in a different video. Okay, so I want to just run this, and then we're basically going to move on. I just want to run this so that we can have one example that sums up a lot of the points we've covered already, but also introduces this new idea of a destructor, and then foreshadows something that we're going to come back to later. And that we're going to talk about when we go through tracing examples. Okay, so here's the output. And I'm going to see if I can display main, all the code for main and the output in the same place. Okay, there we go. So I say starting main, and you can just barely see that off screen up there. Starting main, and then I call parameterized constructor 1. That would be the constructor that takes width and height. Parameterized constructor 2, the one that takes a string for no particular reason. Then I call the default constructor, because that's happening inside of the createUnitSquare function. Then I print out R1, I print out R2, I print out R3, and then I print done main. But that's not the end of the output for the program. In fact, I have these three rectangles. They are about to be destroyed. And when we saw earlier that we defined what is called a destructor for the rectangles. If a destructor exists, it is now part of the normal lifespan of the rectangle. And so whenever a rectangle comes into being, I should expect that at some point in the future, the destructor for that rectangle gets called. And so here I have my three rectangles. Here are the calls to the three destructors. In the destructor, if we scroll to the destructor for rectangle, it prints out destructor, and then it calls the print function on the rectangle, the member function called print, which prints out the width and height, which allows us to see exactly which rectangle is getting destructed and in which order. That's significant for two reasons. One of which is we really care about the order of construction and destruction in this course, and so it's going to follow us through until, well, I guess the rest of the course, but certainly for the next couple of weeks. But also, it makes an interesting point about what I'm allowed to do in a destructor. I mentioned in an earlier video that a constructor, besides the special circumstances under which it is called and the fact that it has no return value, a constructor contains ordinary code. It is an ordinary member function in every respect besides the weird circumstances under which it is called. I can use the member functions, I can use member data, I can use global variables, I can generate output, I can do anything I could do in any other member function in a constructor. The same is true of destructors. Anything I can do in a member function, I can do in a destructor. I can use the members of the class, I can generate output, I can call other member functions. This is significant because it helps us understand when does the data inside the class get destroyed. Well, the destructor is part of the destruction of the class, certainly. But because I can do anything I want inside the destructor, including use the member data, it stands to reason that the members themselves can't get destroyed until the destructor is done executing. And we can see evidence of that down in when we run main. When I run main, when these destructors finally get called, so after main returns, I first destruct the rectangle that was width 1, height 1. Sounds like that's the one that came back from createUnitSquare. Then I destruct the one that has width 10 and height 17. And if we recall, width 10 and height 17 is what's produced by this contrived string constructor. And finally, I destruct the one with width 6 and height 10. That's this one. You'll notice that the destruction order is the reverse of the construction order. And there are very good reasons for that we're going to unpack over the next couple of weeks. And that is a rule. If I construct objects in a particular order, they will be destructed in the reverse order. This rule is a special case, which I guess we could begin defining laws of construction and destruction. The first such law I will summarize by calling it socks and shoes. We're gonna hear ourselves saying socks and shoes over and over in the next couple of weeks. If you put your socks on first and then your shoes, you have to take your shoes off first before your socks. You have to do it. That is the only order that makes any sense. And we'll discover over the next couple of weeks that that is the only order that makes sense for construction and destruction. It is forced by the circumstances. And we can see evidence that that's the rule that's followed here. The destruction order is the reverse of the construction order. And so we're going to begin unpacking that. We're going to begin by first talking about things like tracing code that involves classes, that involves objects with constructors and destructors, and watching how we can use constructors and destructors in classes as a way of proving what we've known all along about the rules of scope, about exactly when objects get destroyed.